One. Good morning, everyone. Welcome to the Toronto Geometry Colloquium. This is a weekly web series all about geometry processing, which aims at promoting young researchers and researchers from traditionally underrepresented communities. Every week, we'll have our opener talking about their cutting-edge research for 10 minutes, followed by a headliner giving us a keynote presentation. We'd also like to send our best to our co-host Sambe, who is currently having a baby. Go ahead, Derek.
So this week, it's our great pleasure to introduce two great speakers. And we have Michal Edelstein as our opener to talk about the Enigma, evolutionary and non-isometric geometry matching. And Julie Digne for learning to encode and analyze and improve 3D shapes. And if you have any questions or you want to discuss anything on these two topics, please leave comments in our YouTube live chat. So our opener, Michal, is a computer science PhD student at Technion, supervised by Professor Maria Benhen. And she obtained her master's and bachelor's degree in electric engineering and physics. And with such a diverse background, you must be curious about what is the relationship between computer science, electrical engineering, and physics. If you are, then you probably come to the wrong place, because today, Michal is not going to talk about the relationship between this subject, but she's going to talk about the relationship between different non-isometric shapes. So without further ado, let's welcome Michal to talk about her SIGGRAPH paper this year on shape matching.
Thank you, Derek, for the introduction. I'll share my screen. Okay, can you see it?
Yes.
Okay, thank you. Okay, so today I'll present our work, Enigma, Evolutionary Non-Isometric Geometry Matching. This is a joint work with Daniel Azuz and Michal Edelstein. So I'll start by explaining what is the problem of shape correspondence. Given two shapes represented as triangle meshes, our goal is to generate as output a correspondence or a map from M1 to M2. So given a point P on M1, we'd like to compute the corresponding point on M2. If we know this map for all the points on M1, we can use color to visualize the correspondence. Matching points are displayed in the same color. The goal is to compute a semantic correspondence between points on the shape so that the knee goes to the knee and so on. Shape correspondence or shape matching is a fundamental task in shape analysis. It has many applications such as texture and deformation transfer, shape interpolation, and more. The difficulty of the shape correspondence problem depends on which shapes we want to match. If the shapes are rigid, we know Euclidean distances are preserved, and the transformation between them is a rotation and a translation, and the problem is much easier. For matching non-rigid isometric shape, like the same cat in different poses, the problem is harder, but in this case, geodesic distances are preserved, and we have a clear criterion for the quality of the map. In the general case, we want to find a correspondence between non-isometric shapes, meaning between shapes that have significant differences, but still belong to the same semantic class so that the correspondence is meaningful, like the giraffe and the horse. In this case, we don't have any prior knowledge that can lead to a clear criterion on the map. And this is the problem our algorithm addresses. There is a large body of work on shape correspondence. Many approaches use user-provided landmarks or are data-driven. Other methods, our method, on the other hand, is fully automatic and requires only the two input shapes, and we therefore focus a comparison with fully automatic shapes. In this talk, I'll show the comparison to four state-of-the-art methods. The first three are based on preserving geodesic distances, which is good for isometric shapes. And the fourth one, BCICP, is based on the functional map framework and switching between functional and pointwise mapping. And the result is a dense map that isn't always locally accurate. So we can consider the problem of shape correspondence as a two-step process. First, the global semantics of the matching is given by a sparse set of corresponding landmark of salient points of both shapes. And if this set is informative enough, it can be extended to a full dense map in a consistent and smooth way. The first problem is combinatorial, whereas the second problem is continuous. Many automatic shape correspondence methods address the first step for the isometric case, and there are many great semi-automatic methods that address the second step for both the isometric and non-isometric case. we propose to combine the steps together and leverage efficient algorithm for solving the second problem to generate a framework for solving the first. Meaning our approach is to find the landmark correspondence that can be extended to the best dense map between the shapes. Since the problem is combinatorial in nature and the objective is nonlinear and non-convex, we use a genetic algorithm that allows us to optimize for it. Our pipeline includes 3 steps. We receive the 2 shapes as input. The first step is finding geometrically meaningful landmarks. The second step is finding the mapping between them, which we do using a genetic algorithm. And the last step is a post-processing step to extract a smooth dense map. So we'll start with the first step. For each landmark, for each shape, the landmark computation is done separately. Hence, we have a different number of landmarks on each shape. In addition, only a subset of the landmark matches. Our goal is to choose landmarks that represent the shapes well and facilitate such a partial match. The next step of our method and our main technical contribution is the computation of the partial landmark correspondence using a genetic algorithm. Genetic algorithms were inspired by natural selection. We have a population of solutions that improves. So they include the following steps. First, a population of candidate solutions is initialized. Then the fitness of each solution, meaning its quality, is evaluated. Next, the filter solutions are combined and mutated, and the new solutions are added to create a new generation of possible solutions. This process repeats until the algorithm converges to a satisfactory solution. When combining and mutating the solutions, the filter individuals are selected from the current population for the crossover where 2 solutions are combined to create new solutions, and for mutations where they undergo changes with a low probability. We designed novel geometric genetic operators specifically for our problem. So I'll talk first about how we represent the solutions. Our populations is a set of candidate solutions. Each solution is called a chromosome and represents a partial permutation. For example, the one we see here. For a chromosome to be valid, it must be injective. Each chromosome is composed of genes, where each gene represents the match of a pair of landmarks. For example, you can see the match of the landmarks on the nose. The correct solution represents the desired semantic match. We want to construct the initial population of valid, meaning injective candidate solutions. For that, we find potentially matching landmarks on the shape and then add them one at a time to the chromosome in a consistent manner that preserves the injectivity until we receive a candidate solutions. And we do it until we get all the solutions in the initial populations. The initial population contains many chromosomes that are incorrect or partially correct. For example, if we look at this chromosome, in some areas, such as the arms, it represents a correct match. And in other areas, like the legs, the match is incorrect. So globally, the chromosome doesn't represent the correct correspondence, but it is locally correct on part of the shape. Since this is just a solution for the initial population, it is good enough. It will improve in later stages. After initializing the population, we need to evaluate the fitness of each chromosome. We need an objective function that will determine the quality of each solution. Our requirement of the fitness function are that it can be used for non-isometric shape matching, as this is our goal. We also need the computation to be fast, and since every solution in each generation should be evaluated. And in addition, the fitness function must be indicative. The global minima should be at the correct feature assignment, but we also need partially good matches to have better fitness than bad matches. So we want to find the landmark correspondence that can be extended to the best dense map between the shapes. We do it in 2 stages. First, we generate a dense map based on the landmark using the functional map frameworks. We choose to use the functional map framework because it performs most of the computation in a reduced spectral basis and is therefore significantly faster. Then we evaluate the reversible elastic energy. This energy was recently used to generate high quality dense map between non-isometric shapes when the landmarks are known. We only measure it and it gives us a good evaluation for the quality of the mapping. And Miri Ben-Chen, my advisor, talked about this energy more in her talk a few weeks ago. And next, we have the genetic operators. After evaluating the fitness of the population, we select the fitter individual whose genes will be passed to the next generation. And we combine and mutate these solutions. The crossover is an operator that merges two input chromosomes into two new chromosomes. We need our crossover operator to produce partial permutation, and we also want it to be geometrically meaningful. Our crossover operator is therefore defined as follows. If we take two different chromosomes, the first with genes marked with sphere and the second with cubes, and combine them, we receive a child chromosomes whose genes are marked according to their origin. Note that most of the genes in the top of the body are from the cubes chromosome and in the bottom from the spheres. Hence, the geometric partial match that existed in a parent is not broken during the crossover. In addition to the crossover, we also design operators for different mutations that change the amount of corresponding landmarks and their value, and those occur with a low probability. And after creating the new chromosome, we add them to the population. We repeat this process until our algorithm converges. And we stop when a maximum number of iterations has passed, or when the fittest chromosome remain the same for several iterations. Here we show the population evolution. The graph on the left shows the energy of the fittest chromosome and the mean energy of the population, both decrease until convergence. And on the right, we show the fittest chromosome and different generation. In this case, the initialization was generally good, but the front legs are switched and the body is also not matched correctly. And the match improves with the generations until receiving the correct correspondence. This concludes our genetic algorithm. Our output is the sparse correspondence of the landmarks and the functional map based on that correspondence. As a post-processing step, we use the functional map as input to reversible harmonic maps to receive an accurate point-to-point map. And now I'll show a few results. So since the dataset contains ground truth sparse correspondence between manually selected landmarks that don't necessarily coincide with our computed landmark, to quantitatively evaluate the result, we first perform the post-processing step to extract the point-wise map. We use the same post-processing for all methods. The x-axis is the geodesic distance between the ground truth correspondence and the computed correspondence, and the y-axis is the percentage of correspondence with less than x error. Higher is better, and you can see that our method outperforms the other methods. And here you can also see an example of the comparison of the resulting landmarks and functional maps with the other method. In this case, the other methods have problems either switching the head of the legs or on the belly, and our method, on the other hand, yields a semantically correct correspondence. And we also compare our results using texture transfers after applying the post-processing to all the methods. And as you can see, the other methods have problems marked in circles, and our method produces good results here and outperforms these approaches. And our method is also applicable to shapes of any genus and can also match between shapes of different topologies, as can be seen here. And in the paper, we have additional results showing the stability of our algorithm as well as the ablation study. So to summarize, we provide the fully automatic method for non-isometric shape correspondence. We split the problem into two parts and compute the sparse landmark correspondence that can be extended to the best dense map between the shapes. To solve this combinatorial optimization problem, we use a genetic algorithm with geometrically guided operators we design. And our method is not limited by the topology of the shapes and achieves very good results. Thank you.
Thank you, Michal, for the great talk. And as usual, and we will proceed to the talk about headliner, and we'll have a joint Q&A near the end. So, and our headliner, Julie Digne, is a researcher from CNRS, and she's also the program chair for this year's SGP happening at Toronto. And her research spans across different topics in shape analysis and geometry processing. And this includes a lot of great works on point cloud processing, such as like filtering or super resolution or like point cloud compression, and a lot more. And basically, when I read her publications, it was like a complete toolkit for processing point clouds. And if anyone is interested in doing like point cloud processing, now is also a wonderful chance because she's also hiring an internship right now on this topic. And today, she's going to talk about this toolkit for processing point cloud. And please join me to welcome Julie.
Thank you. Thank you a lot for this nice presentation, introduction. So I'd like, do you see my screen okay?
Yes.
Okay, good. So first, let me start by thanking the organizers for the invitation. It's a pleasure to present this work at the Toronto Geometry Colloquium. And my talk will be about point clouds, of course, and how to encode, analyze, and improve 3D shapes. So the data I'll handle is typically the one we are used to in geometry processing. It's 3D surfaces that are acquired by different ways, such as triangulation laser scanner, LiDAR, multi-view stereoscopy, depth camera, and so on. And as for the representation, I'll focus on point sets, but many ideas can be extended to meshes or implicit representations and so on. Also, we have like a huge variety of ways of acquiring a surface. We still need tools to to improve their quality, their resolution, and to represent them efficiently. And that's what I try to do in this talk. So the main idea, the property I'll exploit in this trade of works is self-similarity. And self-similarity is something which is a property which is shared by many surfaces with their made by man, designed by human beings, or natural surfaces. For example, if you take the bark of a tree, you'll see that it's a natural surfaces and it has many repeated details, and this repeated detail is what we call self-similarity. Same goes for this stone texture, so it's geometric texture, and it's you have a lot of repeated structures, and this is what I will try to exploit in these works. Of course, the same goes for surfaces for buildings made, for example, by man. So it's a part of the city of Lyon where I live, and you see that all the buildings are a lot self-similar, which is of course something that the architect looked for. And the same goes also for small objects like sculptures or something like that, because there is always some small patterns, for example, the hairs here, which are repeated, which are something which is repeated. And the idea is that we're going to take into account these repetitions to be able to do some early surface processing. So the idea is really that if we have a surface which is self-similar, so which has repeated details, then one acquisition of the shape with these repeated details is equivalent to several acquisitions of the same detail. And we'll find ways to make all these virtual acquisitions collaborate so as to enhance, improve the detail. So we need two necessary ingredients. The first one is a way to compute descriptions of neighborhoods, of small parts of the surface. And the second one is a way to assess how these neighborhoods are similar. And we'll try to extract similarity either from the set of descriptors, either explicitly by performing nearest neighbor search, so most similar neighborhood queries, or implicitly by learning something, by learning some dictionary, by learning some representation, and this dictionary will only be able to exist because of the self-similarity. So we'll need first, in the first case I'll handle, which is a surface case, we'll need some initial working assumptions. So a surface case is the one everyone is used to. It means it's a two-manifold. It's really just a surface, a real world object surface. And then at the end of the talk, I'll extend to other types of surfaces, and we'll see how we can do that. So there is a topological condition that the surface should be covered by a set of topological disks of radius r, centered about around certain seeds. There's a sampling condition which states that our neighborhood of a seed should contain enough points, and a noise level condition which states that the radius r should be above the noise magnitude. So actually what those three conditions state is that it should be a real surface. We should have a scale which is defined, which has some topological consistency, some sampling consistency, and which allows to handle noise. And although it's not at all trivial, I'll do the following assumption. I'll assume that we know how to compute the local intrinsic coordinate frames, so the two principal directions and the normal. And we can compute that for each point of the surface, and just not for the sake of not spending too much time on this issue. So, but we can discuss that in the end if you want. So what about local shape descriptions? It's the first ingredient we need. Initially, there have been works on local shape description for the past 30, 40 years at least. And they were initially designed for partial or complete surface matchings. For example, to do scan registration, to do non-rigid registration, to recognize shapes in databases. For example, here I show one of the maybe oldest local description I could one of the oldest shape description used, which was the spin images. And it represents locally the shape as a histogram, a 2D histogram of two quantities that are computed locally. And the idea were really to match across different shapes or different scans. And here we're going to use that to compare neighborhoods of points on a single shape. And if you forget about the whole set of works of the last 40 years, you can try to come up with the most natural, the most naive, the most straightforward descriptor, which is computing locally a local height field over some smooth surface. Why is it the most natural descriptor? Simply because then you'll be able to, you'll have something which looks like an image. It will be a function defined over some basis, and this way you're closer to image processing than you were before. So it's something which we like because there are a lot of nice image processing algorithms. So let's have a look at the most naive of naive descriptor, which is a plane plus height descriptor. So you fit locally a tangent plane, so you find the tangent plane, and you encode the height over the tangent plane as a function, and you rasterize it over a grid. And then you get a vector in RG, and you can linearize that as a vector in RG. And as a descriptor distance, you can use any metric between vectors in RG. And the thing is, this descriptor already allows to perform some very nice tasks, even if it's a very naive one. But there is a catch, because if you have some large scale curvature over which your detail is bent, then the curvature will be encoded in the descriptor together with the detail. So for example, here you see that there is some large scale curvature, and still it's encoded within the descriptor because it's because the height plus plane does not remove the large scale curvature. So we might miss some similarity. Okay, to alleviate that, there's another naive approach we can use, which is to fit a quadric plus height descriptor. And to do that, we just, instead of finding the tangent plane, we'll find the local regression quadric and fit and represent the local surface as a height over this quadric. And if we do that, it's slightly more demanding in terms of coding, but it's completely doable. We'll still get a height field, height function over a grid. Also, the grid is deformed to fit the quadric. And as a distance, we can still use any metric between vectors in RD. And it's quite, so it's the same kind of algorithms can be used. And and in that sense, we'll be more oblivious of curvatures. So let's start with these two naive descriptions and see what we can do with them. So the first thing we can try is denoising, because when you have real world data, usually it comes with noise at various scales. It can be huge noise or small noise, but it's still something we'd like to avoid. And the idea I would like to extend here is the one from non-local means, which was a nice work from 2005. And the idea was to, so it was an image processing denoising algorithm. And the idea was to denoise a point, not only by considering its neighborhood, as a bilateral filter would do, but by taking into account any point on the image which would look similar. And if we translate that for surfaces, it means that we denoise a point P by considering all points of the surface and weighting their contributions by their similarity to P. And the way we're going to compute the similarity is by describing the neighborhoods and comparing them. And this, so what we'll do here is use plane plus height descriptor, simply because since there is noise, the quadric fitting is slightly less robust than finding the tangent plane. So finding the tangent plane is usually what we do. It's usually more robust. So we'll compute these descriptors, find similar ones using nearest neighbor search, radius search more precisely. And then we are going to weight the contributions of the point P to denoise, of all points of the surface to denoise P. So the question is, what do we denoise exactly? And what we denoise is, instead of denoising directly the positions, we'll do something we'll use a little trick. We'll write the surface as a smooth surface plus some vector field. And the smooth surface will be obtained simply by Laplacian smoothing, for example. And then we'll denoise V using this non-local means approach. And this way, we'll be able to recombine the denoised vector field with a smooth space and recover the denoised surface. So I'll show only a few results, but with real world noise, not the ones that not Gaussian. Not added Gaussian noise. So here is, for example, a set of very geometrical shape. And here are the results obtained by Laplacian smoothing, APSS, bilateral filter, and similarity denoising. So the approach I'm presenting here. And you can see that only bilateral and similarity denoising are able to really remove the small noise we have, which is due to scanner misalignment and so on. And bilateral is of course designed for these features, sharp features between planes. So it's in a way it's very good that it performs well in that case because it's what it was designed for. And similarity denoising also manages to remove the noise and preserve the sharp features. Okay, that's an easy case. Another case which is maybe a little more challenging because there are details and noise. And here is a part of a church acquired by a LiDAR scanner. And here you can see that there is a lot of details, but some very small noise. Well, not very small noise, but some noise well, the acquisition is noisy. And if you use similarity-based denoising, then you manage to remove the noise and preserve the details. Of course, there is a huge problem near the boundaries, so that's one of the disadvantages of using such methods. Okay, so that's when we have noise in our data. Now, what if we have just a scanner which has not the resolution we'd like, something for which we'd like to improve the resolution? To do that, what we try to do is, what we're going to do in a nutshell is to detect details, repeated details, although they are, even if they are bent with different large scale curvatures, and then try to see, and then try to aggregate all this information. So we'll detect that those details are similar, then merge them together and bend them, merge them together, and then put them back at their original places. So rebend them in a way and put them back at their original places. And in this case, you can see that the resolution is improved because all these details have collaborated to be better, basically. So the real question, so the computation of the patches is done by a quadric plus height, descriptor. And then you query over the similar patches simply by using a radius search in the space of patches. And then once you have all these descriptors, unbent descriptor, then you want to aggregate their information. And to do so, we'll do the following. We compute a high resolved grid on P's quadric. So we have a patch P, which is a query, and we'd like to compute a high resolved grid on P's quadric. So that's something we can do. And then we'll aggregate all the points from all the similar patches using this kind of formula, which is nothing to worry about, actually. It's very simple. We compute the high resolution grid height. And to do that, we'll weight each similar patches by their similarity weights. So it's something which depends on how similar the patches are, which is larger if the patches are similar. And then I will aggregate the points of similar patches, of all the similar patches. And that's it. That will define, that will give you a way to interpolate the height of the high resolution grid bin using the different details. And just by doing that, we're able to improve the resolution of shapes. And so here is an example where you have a low resolution shape here on the left, and on the right, you have its super resolution using this approach. And you can see that, of course, it's a nice example because you have a lot of repeated details. For example, here on the left, you have this kind of grid, which is repeated at different places. And this allows to really make everything collaborate. Of course, one reasonable question is to ask whether the super resolution does better than simply using an interpolation, powerful interpolation technique. And it's a very valid question we need to address. So let's take a shape. Let's smooth it out and subsample it. So we degrade it basically. And then let's compare, for example, the quadric super resolution with what would a very powerful interpolation method, robust iterative moving least squares by Osterli in 2009, and see how that works. And what you can see is that, especially near the eye or near the knee, you can see that the details are much better preserved, much better restored using super resolution. So super resolution is actually doing something more than just interpolating from the neighborhood. So that's reassuring, of course, because that was our intent. So here is a small close-up, so you can see better. It's point cloud rendering, so it doesn't look so nice compared to the meshes, but it's also a fairer comparison in that sense. And of course, something we should be aware of is that super resolution is never going to retrieve the exact same surface as we had at the beginning, simply because it's going to find a plausible surface under the self-similarity hypothesis. So it's not going to be looking for, it has no way to retrieve the initial surface, but try to find something which is plausible. So comparing in terms of PSNR, the resolution, super resolution result, and the initial surface is something we can do, is something we do for quantitative evaluation purposes, but in a way, it has no real meaning. It just means that you're not going too far, basically. Okay, there's another problem we can tackle with self-similarity, which is point set compression. Why? Simply because if you have repeated details, then why should we encode them several times? Let's just encode it one time and say this detail is repeated at this position and that position and so on. So that would be the general principle. Of course, it's not that easy because details are sometimes change a little. So we need something a little more fancy than that. But we can still, we're going still to extract self-similarity by learning a dictionary out of a shape. And the way we're going to do that, so the general pipeline would be to take an original surface, so a point set which samples a mathematical surface. We'll sample seeds and derive patches on them, find a parameterization of the patches, and then we'll encode, we'll find the patch descriptions. And these patches, these descriptions, these vectors, will be simply decomposed into a dictionary, a small dictionary, and a sparse set of coefficients. And because the shape is assumed to be self-similar, and the shape is self-similar or else it wouldn't work, then you can find coefficients that are sparse, meaning that you have a lot of zero coefficients, and you can just pick only a few atoms are necessary to represent each patch. So the core component, of course, is how do we compress the patches. And to do that, we'll just state that we need to find a dictionary composed of D atoms over which the plane plus height descriptor, so we used plane plus height, but we could have used any other descriptor, over which plane plus height descriptor can be represented as a sparse linear combination of the dictionary atoms. And this can be formulated mathematically as minimizing the representation error y minus d alpha, subject to the constraint that the number of non-zero coefficients in alpha should be less than some prescribed threshold. And this is actually quite a usual dictionary learning problem, which is usually solved, which can be solved using the powerful KSVD algorithm. And KSVD, if you haven't heard of it, is a two-steps dictionary learning algorithm, which was found in 2006 by Michal Edelstein. And it proceeds in two steps. First, it codes, so you fix the dictionary and you find the best representation of each sample. So you basically compute a sparse code, and that's usually done using orthogonal matching pursuit. And the second step will be to update the dictionary by atom, and this is done by solving for minimizing a Frobenius norm, and you can find the minimizer as a solution of some SVD decomposition. So hence the name KSVD. And if you look at what the dictionary looks like, so here are two shapes. It's a geometrical shape on the left and an artistic shape on the right. And you can see that the kind of atoms that are found out of this dictionary building, the dictionary learning stuff, is really adapted to the shape. It has nothing in common with what we have when we do for example, when we use the Fourier basis or something like that, where the basis is fixed, whatever the shape. Here we have really a basis which is small and adapted to the very shape you're processing. Of course, there are some further compressions that can happen. For example, we can compress the seeds using cavity tree compression. We can compress the local parameterization using predictive coding, and we also compress the coefficients using scalar quantization followed by entropy coding. The coefficients are already sparse, so they are already not very expensive to encode, but using scalar quantization and entropy coding compress it even further. And if we look at this point set, for example, and how in the decompression, so the decompression is actually very easy to do. You just take your the set of seeds, the set of local parameterizations, and then you add the points that are out of the dictionary reconstruction. So it's quite easy. And if you look at this compression decompression experiments, you'll see that the error introduced is less than 1 millimeter. The size of the bit size is less to 2.5%, and the error is less than 0.003 of the diagonal. And actually, the error is only due to, well, is mostly due to removing this kind of scanning misalignment artifacts, and which is in a way normal because it's a kind of a stochastic noise, which cannot be encoded into the dictionary. So it's normal that it should be removed. But yet, the details, for example, the hairs of the Anubis, are very well preserved. Okay, but there's still a catch, because what if we break the working assumptions? Meaning, what if we have a shape with boundaries, with lines and things like that, and we try to compress and decompress it? If we try to do that, what we have is a set of, well, when you have boundaries, what will happen is that the boundaries will tend to dilate, and this will create this kind of weird blobby artifacts. And actually, this is due to the fact that the descriptors, the naive descriptors we used, have no way of encoding a boundary. So that is problematic for this kind of LiDAR data, where you have a lot of boundaries due to occlusions, due to windows and so on, in cities and so on. So we need something slightly different. And this case is what we call a mixed dimension shape case. And if we look, so the boat here is actually a typical example, because it's a shape which contains both surface parts and linear parts. And if you look at it, if you look at it from very close, you would see that actually the ropes are not lines. It's a set of surfaces as well. But at the scale at which we are acquiring the surface, it's better to see them as lines and try to process them as lines. So the intrinsic dimension varies, and we need to be able to handle these cases. So we need to find a descriptor which is basically able to represent surfaces and non-surfaces case as well. So what the idea we developed is to use local probing fields. And local probing fields is basically a way to encode not the shape directly, but the transformation to go from a generic pattern represented in blue here to the local shape. And we attach it to what we call a target area. So it will always represent the same area. So for example, this generic pattern will represent this area here, and so on. And so instead of encoding the shape directly, we encode a set of deformation fields. So what we need is a probing operator, an operator which associates a point in the ambient space to a point on the shape. And we need also a generic pattern, which is a set of points that are sampled inside, for example, a disk or a sphere around the seed point S. And what we'll define is that if we take a point S in the ambient space near the shape, we'll define its LPF as projecting each of the generic pattern points around S onto the surface. So it's a set of vectors. We will have a set of 3D vectors. And now, how are we going to go further with that? Well, we're still going to analyze to find the shape similarity, and to do so, we're going to perform a joint analysis of the LPFs to try to see what comes out, what is the repeated structure, and in the hopes that lines will be detected, will be represented as lines and surfaces as surfaces. So it's a dictionary learning problem once again. So we learn a dictionary of diatoms that best describes the set of local probing fields, a sparse set of coefficients to decompose each local probing field on the dictionary. And what is rather new is to learn also positions and orientations of the local probing fields to best enforce a consistent representation. So it means that we are going to not only optimize for the representation itself, but also for the description itself. So it's slightly different to what is done usually. So how can we formalize the problem? So we have this minimization, and if you look at that from far, here you can find the traditional dictionary learning problem with a small difference to compared to before, where here you have this term here, the L1 term, is a way to it's a way to promote sparsity of the coefficient alpha. It's slightly better to, well, it's more convenient to use the N1 norm instead of L0 to avoid any the non-convexity and so on. So it's better. And then what is new is to also encode, to also optimize for V, so as to make them look closer to their dictionary decomposition while still representing the same area and still covering the whole shape. So we learn not only the dictionary, but also the best location and orientations of generic patterns all over the shape. So the way we solve that is actually quite simple. We iterate 3 steps. We solve for the dictionary and the coefficients, minimizing the dictionary learning problem. So we fix the vectors V, which represents the LPF, and we solve for the dictionary and the coefficients. Then we optimize the pose of the local probing fields by solving for the rotation and translation, minimizing the representation error. And third, we update the LPF by using the new pose and computing and using the probing operator to recompute the LPF. If you look at those 3 steps, 2 first steps are guaranteed to make the energy decrease. The third step can provoke a small increase in the energy, but actually, in a way, it will still, in general, decrease, and it will still converge to some value. So if we look at what happens on the toy example, so here is a sinusoid, and you can see that at the beginning, we spread a lot of different local probing fields on the surface, and they are completely random. So there is no principal direction computation or so on. It's just completely random. And then we run our algorithm, and over the iterations. So over the iterations, what you can see is that the pose tends to align so that similar things are represented in a similar way. And that's really what we aimed for. And if you look at the dictionary, which comes out of the learning process, you'll see that there's one prevalent atom, which is really the sinusoid, a kind of sinusoid atom. So let's look at some test shape. For example, this hollow cube crossed by a line. And here you can see that in the dictionary, you find an edge. And you also find a kind of degenerated atoms, which tends to degenerate to a line. And this will be used to really encode the line here. So let's look at application, for example, shape resampling. So we replace each local probing field by its decomposition to get a consolidated representation. And then we can sample from these local probing fields very easily. And we consolidate, I will not go into details, but we can consolidate between all overlapping local probing fields to have a better resampling. And this way we are able to resample from shapes while still preserving boundaries. For example, the windows are not filled in. So this one is filled, but it was filled in the original data set, and so on. And so what really will drive this sampling is just whether it makes sense, whether the local neighborhoods make sense as with respect to other neighborhoods. So here is the boat I showed at the beginning, and you can see that we can resample very nicely, well, more or less nicely, let's say, the ropes and rigging, whereas other methods tend to either enforce some local surface or tends to blurry a lot the details. And the other application we can develop from that is to denoise shapes by using dictionary learning. And the way we do that is to look for the denoise shape S, starting from S0, this the noisy shape, and enforcing that the denoise shape is close to S0, so that attachment term. Then asking for the local probing fields of the denoise shape to be close to the dictionary decomposition, and of course the sparsity condition that we had before. So how do we solve that? We fix a shape, we learn the dictionary coefficients and positions and orientations, and then in the second step we fix the dictionary and the coefficients, and we find the best denoise point set, and we iterate, and so on. And if we do that, we find that the first step is actually what we did for shape analysis, and the second shape actually breaks down to averaging proposed denoise position. So if you write the mathematical development of this minimization, you'll find that it just breaks down to computing an average. So it's pretty easy. So if you do this denoise, if you experiment with this denoising, you'll find that on most shapes, on most surface shapes, like real surfaces, it performs okay. It may not be the best denoiser ever, but it performs decently well. So for example, here is the Brassampouy shape with added noise, which noise of 0.4% of the diagonal. And if you remove the noise using bilateral filter, robust iterative moving least squares, L0 denoising, or weighted locally optimal projection, well, you find that you get this kind of results. And actually, LPF tends to perform almost as well as WLOP, or as well as WLOP. It's more or less similar. But it's not where it's most efficient. Where it's most efficient is with shapes, of course, which have both surfaces and lines. And in that case, you'll find that basically using LPF, the local probing field denoising, is the only one that will be able to remove the noise both from the surfaces and from the lines. So if you look at the noisy version, so here you have the original shape, you add a noise, and if you compare with all the other methods, then you'll find that some manage to denoise the surface, some manage to denoise more or less the lines, but none of them manage to denoise both efficiently. So I've come to the end of the works I wanted to present today. So what drove this thread of work is basically to do data-driven single shape analysis. So it's still learning, but restricted to a single shape. Of course, we could extend it to using many shapes and different shapes and try to make them collaborate together. But I think it's important to have methods that are able to process from a single shape. So there are many more similar topics to tackle in the coming years. And of course, you might feel frustrated that I didn't do deep learning for point clouds yet. And that I didn't say the word deep in this talk yet. So let's say it now. So deep learning for point clouds, it's something which is growing, something that is now very, very efficient. So PointNet, for example, is a seminar work. More recently, I like the DiffusionNet paper, which was released a few weeks ago, I guess. And the question I'm still not really able to answer is whether they are ready for dealing with very early processing tasks, such as super resolution and so on. So that's something we're investigating right now. And of course, I'd like to say that all these works was done using in collaboration with many people, including Sébastien Valette, Raphaël Chen, and one of my former students, Azouz Amdi Sherif. And that concludes my talk. And if you have any questions, I'll be very happy to answer them.
Thank you, Julie and Michal for the great talks. And we'll stay for a few more minutes to ask some questions from the audience. And in the meantime, if you have more questions, please continue to post your question in the YouTube live chat, and we'll go through them as many as possible. So first, let me start with a question for Michal. So someone asked, is there a specific reason why you choose to use genetic algorithms as opposed to other optimization algorithms? Like basically, what's the property of doing genetic algorithms for this Enigma paper?
Okay, so the problem we're trying to solve is to find the landmark correspondence that can be extended to the best dense map. So our problem is combinatorial because we're looking for the landmark correspondence, and the space of solution is very big because we're looking at all the possible partial permutations between the landmarks. And our energy is the quality of the dense map that was created based on those landmarks. So it's non-linear, non-convex, and it has a lot of local minima. So a genetic algorithm is good for this sort of optimization where it's hard to optimize directly for the energy, but it's easy to calculate the energy and to phrase the problem in a combinatorial way. So that's why we use the genetic algorithm.
I see. So for this kind of problem where we have combinatorial in nature, or we have some very complicated energy function that we cannot, for example, know how to calculate the gradient or the Hessian, then perhaps in this case, genetic algorithm will be suitable.
Exactly.
Okay, understood. And next is a question for Julie. So someone asked whether this like is in the earlier of your talk, like about like filtering the point clouds. So they asked whether this could be useful for like developable surface smoothing and oversampling. And is it all we need to have a filter that takes a neighborhood of the point cloud and turn it into a developable? Like whether we can use your the method similar to yours to like create developable surface or developable point cloud.
Well, not really, because if you want to compute a globally a global parameterization of your point cloud, you need something further than this is very local. And actually it's a problem that is very local because sometimes there is some, because of sharp features, the scale you choose, the analysis scale you choose is not enough to, is not suited to the sharp feature, and this provokes some artifacts. And using them, iterating it to find some global developable surface, I think you'll stumble on this kind of issue very quickly.
Oh, so basically we need some global information in order to do that? Is that what? Yeah,
probably. Okay. I think I'm not sure iterating such a filter would be I think at some point, well, it's the same kind of issue you'd have with iterating a Laplacian filter or something. That's at some point, you'll have some topological problems and you'll have some artifacts that will arise.
Okay, thank you for the answer. And next question is for Michal. Someone asked, is a landmark selection by your algorithm correspond to some semantic features of the shape or some geometric feature of the shape?
Yes, so I didn't get in at all into how we calculate the landmarks, but yes, we needed landmarks that represent the salient points on the shape and also that represent the shape well, but also not too many landmarks because then the problem becomes too big to solve. So we use a few methods that allows us to get this kind of landmarks, and the details are in the paper, or if anybody's interested, you can email me later.
Okay, thank you for the answer. And next is for Julie. So, okay, so someone asked about your self-similarity measure. So, and they ask whether this measure will change with respect to the resolution with point cloud. Would everything become like more self-similar when we work on, for example, the higher resolution point clouds?
Yes, it's a very good question, because of course, if you take a very small scale, well, provided you have enough points to do that, you take a very small scale. Of course, everything will be similar, because, well, it will be mostly a plane or some noise, and it will be very difficult to distinguish between a noise in a well, different sampling of the noise, basically. So there will be no real, I mean, everything will basically have the same similarity distance. So there's a question which I didn't really talk about in this talk, with to which scale should we choose so as to have a good analysis. And that's an open issue for now, at least. So right now it's try and see what comes out of it.
I see. So perhaps the kind of the window size for you to measure similarity, it's also like a important parameter for the algorithm.
Yes, it is. But what we usually do is have, of course, a weighting, a Gaussian weighting, Gaussian decay, so that it kind of alleviates the need for a hard threshold.
I see. I see. Thank you. And the next question is for Michal. So since your algorithm Enigma is like targeted for a very challenging problem like non-isometric shape matching, and just curious, like in your experience, is your method has any failure cases, like have some non-isometric shape pairs that you get like the result that are surprisingly bad?
Yes, so because the way we extend the landmark correspondence to a dense map is using a functional map with a relatively small basis, then we're limited by what this basis can represent. So we saw, for example, for shapes like ants that have a lot of, like the hands are very thin and it has a lot of hands, then the functional map isn't able to represent it well, and we get a lot of switches between the hands and this kind of artifacts. And then the correspondence we find isn't correct. I mean, we still find the lowest energy, but the lowest energy is for an incorrect match.
I see. So probably your algorithm depends on how like the functional map, the quality of a functional map, right?
Exactly.
I see. And that reminds me, perhaps like a recent SIGGRAPH Asia paper on map tree could be something useful, which consider all the combinations of the possible like functional maps.
Could be interesting.
Okay. Yeah, okay. And the next question is also for Julie. And so okay, so your method also your methods for like the patch self-similarity reminds the people about like the patch match algorithm for image processing. And some people wonder whether your method can be used for tasks like a point cloud hole filling or point cloud recarditing, similar to how patch match works on images.
Yeah, it's a very, very good question. So patch match actually makes the whole similar patch query very fast. And that's something we didn't do yet for various reasons. I will not go into details right now, but it's kind of difficult. It can be used in painting or filling holes and so on. There's a catch though, because when you do an image based in painting, you'll have a grid and you know where you want to put the pixels. When you have a surface, then if there's a hole, you don't know the topology of the surface inside the hole. And first, I think what a reasonable way of doing in painting would be first to have some smooth, like a Laplacian or simplet spline hole filling method, and then to add details using self-similarity, for example. And that would, could be a way to make it work. But there's this early step we need to do, which is not necessary for images, but we need to do that for surfaces. But yes, we could do that.
I think that's actually a good point. Like when you want to do matches on the point cloud, it's unclear because you also don't know what the underlying surface without like filling a hole. Yeah. Okay, and the next question is also for Michal. So have you considered to extend your landmark representation to the continuous setting, basically represent the landmarks as a barycentric coordinate on faces? Like, is there any benefits of doing that?
You mean just move the landmarks to other points, or?
Yeah, so if my understanding is correct, your landmarks currently select as some subset of vertices. Yeah, is it possible to represent a landmark as like the point in the middle of a triangle represented as a barycentric coordinate, so that you can kind of continuously moving the point across the entire surface in order to find a better landmark matches.
So right now, though, we compute a set of landmarks in the beginning, and they stay fixed for the entire process of the algorithm. So I think we can change the algorithm to choose landmark in the beginning that don't necessarily have to be on vertices. But it could be also interesting to try to improve them or something like that, but that would be more complicated, I guess.
That's right. That's right. If you work on like continuous setting, you have more things to optimize.
Exactly.
Yeah. Okay. And next question is for Julie. So someone asked, is the information you use for like the ships at near the end of your talk, is it those information can be used for extract some simplicial complex like triangles or like the polylines, basically using it for like point cloud reconstruction?
It's not, yeah, it's something we try to think about, but it's not so trivial because this really encodes the geometry of it, and the local probing fields only encode really the geometry, and reconstructing the simplicial complexes out of it. It's really, I don't see how you can bypass, how this can help bypassing the surface reconstruction. The thing you can say is still whether locally you should fit a line or fitting, sorry, a set of edges or fitting a set of triangles. So in that sense, it could help, but choosing which triangles go where, I don't see how this can be done efficiently, but maybe there's a way, but I don't see it.
Okay, thank you for the answer. So sorry for those questions that we don't have time to go into because we are like over time already. So now let's thank you everyone for coming to this colloquium, and let's thank our speakers again. And we also want to thank the artist, Scott Carmichael, for making the great poster for this week. And next week will be our last colloquium for this season, and features by Sheldon Wei and Rosa Maria Sanchez. See you all next week.
Okay.